Now we're going to look at the data environment, how we can modify where data is stored and how it can be shared or privatized and so on. So the default environment of data is that data is shared. So most variables are shared by default. For instance, global variables are shared by default. So these are variables that are defined as file scope variables in C or static, but they could also be variables that are dynamically allocated with malloc or new or anything else. Could also be variables that are declared outside the parallel region in the same function as the parallel region. But not everything is shared. So as I mentioned earlier on, stack variables in functions are privatized, and automatic variables within a statement block are also privatized. We'll see examples of that later on. So here is some example. Look at this code here. We have a variable A here outside at file scope level. We have a variable index inside the function. We have a parallel region. It works on the index, and then after the parallel region we print some variable here. Okay. Then we have a function. So the parallel region calls a function work, which is in a different file. We declare A so that you can access A here. We pass the pointer to index here. We have a variable temp, an array declared here, and a static int count declared here. So, file scope variables, that's A here, that's shared by all threads. Index is declared inside this main thread here, and it will be shared for the threads inside the parallel region here, but normally file functions in a different file will not be able to access this index. They can't name it. But in this case, we pass the pointer to index to the function work, and therefore index is also shared here. If work function here access index, it will be the shared variable on the stack of the main thread here. Count is declared static, and therefore by default this is also a shared variable. So if the different threads use count here, it's the single scalar shared variable count it will be using. On the other hand, temp is declared inside the function here. Therefore it will become on the stack on every thread that start to execute work. So temp will be private for each thread. Okay? You can change how things are accessed and stored by using different storage attributes, and the most common ones are used shared, private, and first private. Shared specifies that a variable is supposed to be shared, and this applies in OpenMP. This is useful only in Fortran actually, because things that are private by default cannot be made shared, but shared variables that are shared by default can be made private. It's opposite in Fortran. Anyway, private specifies that a variable that otherwise would have been shared is going to be private for a thread. First private is the same thing, but it will copy the value of the shared variable to each thread's private variable. Last private can be used for loops. It will copy out the value of the private variable. So it's the same thing as private, but it will make the shared variable take, after the for loop, take the value of the private variable of the thread that executes the last iteration. There is also a way to override the default attribute by specifying default shared, which is the same thing in C. A default private can only be used in Fortran, and default none, which enforces you to specify for every variable if it's going to be shared or private, which I recommend strongly. So let's have a look at the private clause here. We specify a variable temp here, declare a variable temp, and we say that it's private, and then we're going to assume each thread will get a private variable, but this is not going to work because we specified only as private, because private will create a new uninitialized local copy of this variable temp, and in this case we rely on temp being privatized. Sorry, we rely on it to be initialized to 0 because it's a reduction variable in this case, so it will not work. The way to do this would have been to change this to first private. So here we see the same thing, but with the first private clause. Then you can wonder what happens with TMP after the loop. So in this case, we have a private copy of TMP. They start at 0, both of them, all of them, and then and they have an initial value of 0. Now, what happens? What value does the TMP have after the loop? And this is actually different in different versions of OpenMP. It usually does. I mean, usually you shouldn't rely on this. In version 3, which is the latest, and later on, which is what you should use, it takes the value that TMP had before the loop here, so it will be 0. Last private. As I said, last private, you can specify first private and last private. So last private on the for loop will make sure that the value of TMP in this case, after the for loop, takes the value of the thread that executed the iteration j equals 999. So j temp will have value 900 and, well, the value of j equals 999 in this case. So you can specify a change in the default behavior. So the default is shared, so you don't need to specify that. But I recommend that you specify default none. So default private is only for Fortran, so that's not meaningful here. But for C, it's good practice to specify default none. That means that you have to specify the storage attribute shared or private for every variable in the static extent. This is good programming practice. So default none, I recommend. And this is useful in particular in this next exercise, which I urge you to do in molecular dynamics. There is a, in the code that you could download, there is a directory, I think it's called Moldin, where you can look at the function forces.c, and you can parallelize this by finding out which for loop this routine and think about which variables should be shared, private, or have a reduction on it. You may want to use tools to find data races, otherwise you need to think where can data races occur and experiments with different schedules.